Welcome to this explainer. Today we're diving into Phoenix, Arizona, unpacking its climate history and looking at a very specific, conditional future. And I promise you, there are absolutely no disaster spectacles here. We are just going to take a structured, objective look at what leading models are telling us, and honestly, just as importantly, what they aren't. The key word you're going to hear today is conditional. By the end of this, you'll know exactly why that matters so much.
Now you might be wondering, why are we focusing on this specific location today? Well, it's because on July 24, 2026, the Climate Place market cleared Phoenix for exactly 88 cents. Now, that financial figure isn't climate evidence in and of itself. Rather, it's a really precise measure of intense market attention and demand for coverage around this exact coordinate, right at 33.4480 degrees north, 112.0740 degrees west. So, since the market is demanding attention here, let's give the data a really close look.
Let's kick things off with Section 1, Reanalysis-Backed Climate History and Trends. To really grasp where Phoenix might be heading, we've got to ground ourselves in its recent past. We're looking at a 45-year historical span, from 1981 all the way through 2025, using NASA Power's MERA-2 dataset. This is highly robust, reanalysis-backed historical data, and it gives us a broad, mathematical look at the temperature environment over time. When you strip away the daily noise of weather, a macro-level shift becomes super obvious. Just look at this. The mean near-surface temperature for the first complete decade of our data was 21.31 degrees Celsius. Fast forward to the most recent decade, that baseline has jumped up to 22.96 degrees. So, taking those two averages, we find a difference of 1.64 degrees Celsius. And if we draw a simple least squares line right through all 45 of those annual values, we hit a historical trend of 0.47 degrees Celsius per decade. But what does this 1.64 degree overall historical increase actually mean for the future of Phoenix? And maybe the better question is, what does this single number completely leave out? To answer that, we really need to talk about how this data is gathered and structured in the first place.
We have to understand a concept called gridded reanalysis values. See, these numbers represent a broad grid cell, specifically a 0.25 degree model grid, that essentially draws a box around Phoenix's coordinates. This is not a specific thermometer reading on your street or someone's backyard weather station. It's a synthesized, mathematical representation of a wide area. It's incredibly useful for tracking macro trends, for sure, but it is fundamentally different from a highly localized record.
And this is absolutely crucial because local lived temperatures can diverge wildly from that macro grid. Things like proximity to water, mountainous terrain, sparse observing networks, and especially dense urban surfaces, all of these completely change what you actually feel when you walk outside. For instance, our grid shows a recent mean daily precipitation of 0.72 millimeters per day for this area. But, as we all know, at the local storm scale, rainfall can vary drastically from one neighborhood to the very next one over. Basically, the grid gives us the canvas, but the local geography is what paints the final picture.
Which brings us to Section 2, the Conditional SSP 5-8.5 Outlook.
So, looking ahead to the 2040 to 2049 projections, we're using the NASA NEX GDP CMIP6 dataset. Remember earlier when I said the keyword was conditional? Well, here is exactly where that comes into play. We are looking through a highly specific lens using the SSP 5-8.5 scenario. This is a high emissions scenario. It is a what-if, based on a very specific high emissions pathway. It is not, I repeat, not a probability-weighted forecast or some guaranteed crystal ball prediction of the future. We are simply asking the models, hey, if emissions follow this specific high path, what does the physics say is going to happen to this grid cell?
When we run this exact same high-emission scenario through three distinct world-class climate models, the results for the 2040s vary quite a bit from their own historical baselines from 2005 to 2014. Even with identical starting points, the Access CM2 model calculates a 2.25 degree increase, MEROC 6 projects 1.72 degrees, and MPI ESM1-2HR projects a 1.35 degree increase.
What's really fascinating here is the spread. We're looking at a range from 1.35 all the way to 2.25 degrees across just this small ensemble of models. And you know what? In climate science, we actually celebrate this variation. Model spread is a healthy, totally essential part of the scientific process. Different models have different structural architectures and mathematical assumptions baked in, so no single model projection should ever be privileged as the absolute prediction. Keeping this spread visible helps us honestly understand the true boundaries of our knowledge.
All right, let's move into Section 3, Limits of the Grid.
We absolutely have to apply a strict reality check here and recognize the critical caveats of these models. First up, while the history definitely supports a directional account of warming, you cannot use this regression to prove why a specific single event, like a freak storm or a distinct heat wave, happened on a given Tuesday. Second, these projections are entirely conditional on the model structure, the bias correction, and the statistical downscaling. Third, they are bound exclusively to that SSP5 8.5 high emission scenario we talked about. And finally, notice that precipitation is completely omitted from the specific bounded comparison. It's just not part of this equation.
But honestly, perhaps the biggest limitation for a place like Phoenix is the city itself. Its urban form, the vast expanses of concrete, the dark asphalt, the geometry of the buildings, and the lack of tree canopy in certain neighborhoods. All of that can locally amplify heat well beyond what our macro-level 0.25-degree grid can ever capture. The model sees a broad grid cell. You experience the heat radiating directly off a parking lot at 3 p.m. Huge difference.
That leads us perfectly into our final section, asking better local questions.
So where does all this leave us? Well, the global macro models give us the broad directional contours, but the reality is they just don't know your neighborhood. By understanding exactly what these models provide and freely acknowledging what they leave unresolved, we're empowered to look a little closer to home. The exact question you should be asking right now is this: what do your city's high-resolution local records, thermal maps, and civic planning documents actually reveal about the future of your specific street? The global models have spoken, but will your local reality be a refuge or an oven? Thank you so much for joining me for this explainer. Now it's time for you to go check your local data.